So, good evening everyone. I welcome you all to the week 10 live problem solving session on mathematics, applications, and algorithms course. So, this week we'll be trying with the protein interactions, which I have discussed last week. So, we'll be focusing on protein ligand interactions and drug discovery concepts. Protein, protein interactions play a crucial role in various biological processes, including cellular signaling, enzymatic activity, and gene regulation. Understanding these protein interactions is a fundamental in drug design, as many diseases are caused by disruptions or dysregulations in these interactions. By targeting specific protein-protein interactions, researchers can develop drugs that can modulate cellular pathways and restore normal functions and offer promising therapeutic interventions. The process of drug design often begins with identifying key protein interactions involved in a particular disease pathway. This may involve techniques such as structural biology, molecular modeling, and high-throughput screening. Once these interactions are characterized, researchers can design molecules and often referred to as ligands or inhibitors, which selectively binds to target proteins either by enhancing or inhibiting their interactions. In this scenario, computational methods are employed to predict how potential drug candidates interact with their target proteins. This allows researchers to optimize drug molecules for improved binding affinity, specificity, and pharmacokinetic properties. So overall, these protein interactions are intricately linked to drug design, serving as a cornerstone for the development of novel therapeutics. By leveraging our understanding of protein interactions, researchers can design drugs that effectively modulate biological pathways, offering new treatments for a wide range of diseases. So, today's interest of studies protein ligand or protein small molecule interactions. So, these interactions encompass a wide range of physical and chemical forces such as hydrogen bonding, van der Waal interactions, hydrophobic interactions, and electrostatic interactions. These interactions determine these interactions determine the stability and specificity of the complex formed between protein and the ligand. Protein ligand interactions play a role in various biological processes, including signal transduction, enzymatic catalysis, regulation of a gene expression. Here we have two types of ligands: endogenous ligands and exogenous ligands. Endogenous ligands are naturally occurring molecules within the body, such as hormones, neurotransmitters, and metabolites, which bind to proteins to regulate the physiological functions. Exogenous ligands originate from external sources, include drugs, environmental toxins, and dietary components. They mimic or modulate the actions of endogenous ligands by binding to the same or different binding sites on proteins. So binding sites are the regions on protein surface where ligands bind with specificity. These sites often possess complementarity shapes, electrostatic potentials, and chemical properties to accommodate or interact with the ligand. A protein may have one or more multiple binding sites, allowing them to interact with different ligands simultaneously or sequentially. Next is pose of binding. The pose of binding refers to the specific spatial orientation and conformation adopted by the ligands within the binding site of protein. This influences the strength and specificity of protein-ligand interaction by determining the complementarity of molecular surfaces and the formation of favorable interactions between the functional groups. Here, the pose of binding directly affects the affinity and selectivity of the interaction, and a favorable pose maximizes complementarity interactions between the ligand and protein, resulting in a stronger binding affinity and specificity. Changes in pose of binding, such as alterations in ligand orientation or conformation, can modulate the strength and specificity of the interaction, thereby influencing the biological activity of the protein ligand complex. Some examples of protein ligand interactions that we see in the nervous system: neurotransmitters such as serotonin, dopamine, and acetylcholine bind to their respective receptors, initiating a cellular response or a neurotransmission. And we also have hormones like insulin. Drugs interact with their molecular targets such as enzymes, receptors, or ion channels to modulate biological pathways and treat diseases. So, which include examples include antibiotics targeting bacterial enzymes and anti-cancer drugs inhibiting the specific signaling proteins. Now that we have studied about interactions, so here is a question for you. So one can answer this using the chat box. So endogenous ligands are. So endogenous ligands, so whether they are naturally occurring molecules within the body or foreign substances introduced from external sources, synthetic compounds designed in laboratories, or proteins involved in catalytic reactions. Yes, thank you for the answer. Yeah, endogenous ligands are not naturally occurring in the body. So the pose of binding. In a protein ligand interaction, the pose of binding refers to whether it refers to the location of the protein within the cell or the spatial orientation of and conformation of ligand within the binding site, or it represents the mechanism of enzyme catalysis or the structure of DNA. So the pose of binding refers to the spatial orientation and conformation of the ligand within the binding site. So this pose of binding helps in matching the complementarity of the binding site, thereby increasing the affinity and specificity of the ligand. So the binding of a ligand to a protein can be described using an equilibrium binding equation, also known as law of mass action. The equation relates the concentration of protein ligand and the protein ligand complex at equilibrium. So we have a term called dissociation constant, which measures the strength of their interaction. So the general equation for protein ligand interaction is protein plus ligand gives rise to protein ligand, which is a reversible reaction. The equilibrium constant for the binding reaction is given by concentration of protein multiplied by concentration of ligand divided by the concentration of protein ligand complex. So here the dissociation constant represents the concentration of ligand at which half of the available protein binding sites are occupied. It is a measure of affinity of a protein for the ligand and with lower Kd values indicating stronger interactions. So this binding of a protein can be influenced by various factors such as pH, temperature, surrounding environment, salt concentration, and presence of other molecules. So these factors affect the shape and charge of the protein and ligand as well as the strength and specificity of their interactions. So coming to the topic of drug design also known as rational drug design is a creative process aimed at discovering new medications based on understanding a biological target within the body. Typically, drugs are organic molecules that either activate or inhibit the function of a biomolecule. The core idea behind drug design is to create molecules that perfectly complement the shape and charge of the biological target they interact with. This complementarity fit allows the drug molecules to effectively bind to the target, influencing its activity in a desired way. So computational modeling techniques play a crucial role in drug designing, allowing one to predict how well a potential drug molecule will interact with its target. This approach is known as computer-aided drug design, which helps in identifying the promising drug candidates more efficiently. So the drug discovery is of process of finding new medications to treat disease. It involves two main approaches: phenotypic drug discovery and rational drug discovery. Phenotypic drug discovery, also known as forward pharmacology or classical pharmacology, which involves screening of collection of synthetic small molecules, natural products, or extracts within the chemical libraries to identify the substances with beneficial therapeutic effect. This method starts by discovering the functional activity of drugs, followed by target identification. It's a practical and target independent approach aimed at finding pharmacologically active components and therapeutics that work through novel drug mechanism. Next, we have rational drug discovery. It is also known as reverse pharmacology. Begins with a hypothesis that modulation of a specific biological target may have therapeutic value. This method requires two informations, that is, evidence that modulation of target will be disease modifying, and confirmation that that target can bind to small molecule and its activity can be modulated. Once a suitable target is identified, it is cloned, produced, and purified, followed by the establishing a screening assay and determining the three-dimensional structure. So here, the search for small molecules that bind to the target involves screening libraries of potential drug components, either to experiments or virtual screens. So the ideal drug candidate should be drug-like processing properties predicted to lead the oral bioavailability, chemical stability, and metabolic stability. So various methods exist to estimate drug likeliness and predict the drug metabolism. One such is Lipinski's rule of 5, formulated by Dr. Christopher Lipinski, which is a set of guidelines used in drug discovery to assess the drug likeliness or the pharmacokinetic properties of potential drug components. These guidelines are based on empirical observations and aim to predict the likelihood of a compound being orally bioavailable, which is crucial for its effectiveness as a medication. So the Lipinski's rule of 5 states that the molecular effect compound should be less than 500 Daltons. The calculated octanol water partition coefficient log P should be less than 5. Here log P is a measure of compound's lipophilicity, or its ability to dissolve in lipid versus water. Compounds with excessively high log P values may have pure solubility and absorption. Then we have the number of hydrogen bond donors, usually represented by the sum of nitrogen, hydrogen, and oxygen hydrogen bonds capable of forming hydrogen bonds should be less than or equal to 5. And hydrogen bond acceptors, the number of hydrogen bond acceptors should be less than or equal to 10. The rationale behind these guidelines is that compounds meeting this criteria are more likely to have favorable pharmacokinetic properties, including better absorption, distribution, metabolism, and excretion, that is, better ADME profile. Specifically, compounds adhering to the rule of 5 are more likely to be orally bioavailable, as they are more likely to pass through biological membranes and reach systemic circulation. So according to the Lipinski's rule of 5, the molecular weight of a compound should be less than 1000 Daltons, less than 100 Daltons, or should it be less than 500 Daltons, or it should be less than 50 Daltons. So according to Lipinski's rule of 5, the molecular weight should be less than 500 kilodaltons. So this improves the absorption, distribution, and metabolism of the drug. The computer-aided drug design can be broadly classified as structure-based drug design and the ligand-based drug design. In the structure-based drug design, this approach involves the use of protein structure to guide the design of drug molecules. It is typically used when structure of a protein target is available. In structure-based drug design, computational methods are used to identify the potential binding sites on protein surface, and then small molecules are designed and optimized to bind specifically to these sites. Ligand-based drug design is used when protein structure is not available and is difficult to obtain. So in this approach, a small library of small molecules that have already been characterized and their binding affinity for the target protein is known or used. The structure of a protein is not considered in the initial phase, and the design of new drug molecules is based on the properties of the known ligands. So the choice of the approach depends on the availability of protein structures and other factors such as size of the target protein and desired specificity of the drug. Each approach has its own strengths and limitations, and sometimes researchers often use a combination of these methods to increase the chances of success in drug discovery. So which approach in computer-aided drug design relies on availability of protein structures to guide the design of drug molecules? Which only relies on availability of protein structure. Structure-based drug design involves the studying three-dimensional structure of a target molecule to design small molecules that can bind to the specific sites on the target, thereby altering its activity and potentially providing therapeutic benefits. The structure-based drug design has several key steps. First one is target identification and selection. Initially, one identifies a specific protein or enzyme which is involved in a particular disease process that could serve as a target for drug intervention. Once target is identified, its three-dimensional structure is determined using experimental techniques, or if it is available, that three-dimensional structure can be extracted from PDB. So this structural information reveals the protein shape, surface features, and potential binding site for drug molecules. Computational methods are then used to design small molecules capable of binding to the target. Researchers generate a library of potential drug candidates and screen them for their ability to bind to the target protein through docking. Or this step helps in identifying promising drug candidates based on factors like binding affinity, specificity, and predicted pharmacological properties. So further, the drug molecules are optimized through various techniques including synthetic chemistry, structural modification, or enhancement of other properties. Once an optimized lead component is obtained, it undergoes a rigorous preclinical testing to evaluate its safety and efficacy. This involves testing in animal models to assess the potential side effects and toxicity. If the lead component demonstrates safety and efficacy in clinical studies, it will advance to the clinical studies in humans. So one main thing is in structure-based drug design is docking, which is a computational technique aiming to predict how a potential drug molecule interacts with the target protein or enzyme. It involves assessing the energetics and geometry of the interaction between the drug candidate and the potential target, aiding in identification of compounds which are likely to bind with high affinity and selectivity. The steps involve The docking process involves preparation of protein and ligand, where the target protein and ligand undergo preparation steps to eliminate interfering elements like water molecules or unwanted residues. Next is identification of binding site. Analyzing the protein structure helps in identifying the potential binding pockets or cavities on this surface, determining where ligand can bind. Next is initial placement of ligand. The ligand is initially positioned within the binding site, and this can be accomplished to various methods such as random placement or utilizing shape-based matching algorithms. Once a binding has been established, the interaction between the ligand and protein is assessed using a scoring function, which evaluates the energy and geometry of the complex. Then we have validation and refinement. Predicted the docked process, where the predicted docked process are validated and refined using experimental data such as site-directed mutagenesis and NMR. So many softwares are available for docking calculations. So before talking about them, we'll go into some other docking steps. In docking, scoring functions play a crucial role in assessing the binding affinity between a ligand molecule and a protein target. The primary objective of docking is to identify the most favorable conformation of the ligand within the protein's binding site, and scoring function offers a quantitative measure of the interaction strength between the ligand and protein. So here are some main types of scoring functions used in docking. Empirical scoring functions. So these functions rely on statistical analysis of experimentally derived protein ligand complex. Parameters describing various interactions such as van der Waals, electrostatic heterogen, bonding, dissolution are weighted and fitted to the trained set of complexes. Then the new docking forces are scored based on their resemblance to the training set. Next we have force field. These functions utilize the molecular mechanics force field to describe the potential energy of a ligand protein ligand complex. So they include parameters defining bond, bond angle, dihedral and non-bonded interactions. Then we have knowledge-based scoring functions such as distance-based potential functions which decide the frequency of observed interactions in the training set. These are like similar to empirical, where docking processes are scored based on their similarity to the training set. Then we have machine learning, where we apply machine learning algorithms to learn the relationship between protein ligand interaction. So initially these methods are trained on large datasets of protein ligand complex, where they predict the binding affinity of new ligands to a protein target based on their properties. So some common programs that are used for docking are Autodock, which employs empirical scoring function; Gold, which uses a chem-score empirical scoring function incorporating 16 terms of representing various types of interactions; Glide uses MMGBS, a force field based scoring function; Flex employs again an empirical scoring function. So the first step in any docking program does is searching for a interaction pose or a complex, the accurate complex structure, then followed by scoring of the complex. So in docking programs, two primary types of search algorithms are typically employed to navigate the conformation space of the ligand molecule and determine its optimal orientation and conformation within the protein's binding site. First is global search, then we have local search. So these global search algorithms explore a vast conformational space, primarily utilized in initial stages of docking to locate the approximate binding site and orientation of the ligand. So they include genetic algorithms, simulated annealing. Then we have local search algorithms, where these algorithms refine the binding mode and enhance the ligand's binding affinity within the binding site. They work by making small adjustments to the ligand's position, orientation, or conformation and assessing the resulting binding affinities. Some docking programs may integrate the blend of both global and local search algorithms to balance the exploration of conformational space with the optimization of binding affinity. The choice of search algorithms hinges on factors such as the size and complexity of the molecules involved and available computational resources. So given that we have discussed about the scoring functions, what is the primary purpose of scoring functions in docking? Whether they are used to prepare protein and ligand for docking or to assess the binding site of the protein or to assess the energetics and geometry of the ligand protein interactions or to validate or refine the predicted docking process. It is to assess the energetics and geometry of the ligand binding. Now, docking is like one protein or one ligand concept. Now we will be entering into virtual screening, which is aimed at pinpointing several potential drug candidates from extensive compound libraries for the docking. So this includes several key steps. So first is target selection, then compound library preparation, where we create a vast database of compounds. Then we have protein preparation and ligand preparation and dogging. So here the prepared components, the several components are docked onto a protein using a sophisticated algorithms. So this step explores various protein ligand orientations, various ligand orientations of protein binding site and evaluates their interaction to calculate the binding affinity. Post docking, the compounds receive scores based on their predicted binding affinity to the protein. Scoring functions, which consider factors like electrostatics interactions, provide the score. Compounds exhibiting highest predicted binding affinity are identified as potential hits, and these hits undergo further scrutiny using computational and experimental methods to find out the most promising drug candidate. So virtual screening harnesses the computational power to comb through the compound libraries and identifying the promising drug candidates and optimize them iteratively, serving as a pivotal step in drug discovery pipeline. So this technique involves several steps. That is, sorry. Now we are discussing about other-based pharmacophore based modeling. So this is a computational technique that's used in drug discovery to identify and design small molecules that bind to a specific target protein. The technique involves identification of key molecular features or pharmacophores. Key molecular features are nothing but the pharmacophores that are required for a molecule to bind to a protein. So in pharmacophore generation, we take the ligand data set that is used to generate a pharmacophore model using a pharmacophore model software tool. The pharmacophore model consists of key molecular features or pharmacophores that are essential for ligand binding to a protein. So the general pharmacophores can be hydrogen bond acceptors, hydrogen bond donors, hydrophobic regions, aromatic rings or other chemical features. The pharmacophore model is validated by comparing it to the known ligands that bind to that target protein. So we know set of proteins, set of ligands that actually bind to the target protein. So based on these ligand information, we validate the potency of the new components that bind to this. Then the generated pharmacophore models can be mapped onto any of the existing small molecule database to extract the molecules that are similarly available. So the following are some of commonly used software tools for pharmacophore modeling. So ligand scout, MAE and discovery story and pharmacist. So in pharmacist, once a pharmacophore model is generated, it could be mapped onto a zinc database to identify the chemical or small molecules that exactly match this pharmacophore. Then we have QSAR, which is again a ligand based. So here initially I discussed docking and virtual screening, which are structure based, pharmacophore and QSAR, which is ligand based. QSAR stands for quantitative structure activity relationship. So in QSAR, we try to predict the biological activity of molecules based on their chemical structure. So QSAR is nothing but a linear equation or a regression models that we build to predict any continuous variable. So the need for QSAR arises from the need to quickly and accurately identify the active components for drug discovery and development. The traditional methods for drug discovery involve synthesizing and testing a large number of compounds to identify those that have desired biological activity. This process is time consuming and expensive and requires a significant amount of resources. QSR offers a more efficient approach to the drug discovery by using computational methods to predict the biological activity of the compounds. QSR models can be used to identify the compounds with the desired activity and reducing the need for extensive synthesis and testing. So what is the purpose of a QSAR modeling? So whether we try to predict the toxicity of the components, or we try to predict the biological activity of the components based on their chemical structure, or we try to synthesize new components based on known structures, or we try to assess the drug likeliness of potential components. Yeah, so they have to predict the biological activity. So the QSAR, the first step in developing a QSAR model is to collect a dataset of compounds with non-biological activity, that is experimentally derived biological activity. The dataset should be diverse and representative of chemical space of interest. Next step is to calculate a set of molecular descriptors for each compound in the database. The molecular descriptors are numerical values that represent the chemical and physical properties of the compound, such as molecular weight, number of hydrogen bond polar surface area, and many others. So these descriptors are used as input variables in QSAR model. The data set is then pre-processed to remove any duplicates, outliers or missing values. So what duplicates does is duplicates makes the overfitting of the model. So why the performance of the model on a new or unseen test set will vary. What outliers test is creating a noise in model training. So the next step is then to build a QSAR model. The QSAR model are based on statistical observations or any machine learning model. So the training set is used to train the model. So the initial data set is divided into training set and a validation set. So the purpose of the training set is where the model will try to develop an equation using this training set. And test set is we try to apply that equation, generated equation to a test set and to see the prediction performances. So there are several types of descriptors that have been available. So these a set of descriptors I have taken from the PEDAL descriptor calculation tool. So we have constitutional descriptors, topological descriptors, geometric descriptors, electronic descriptors, hydrophobicity descriptors, quantum chemical descriptors, and pharmacophore descriptors. So of these, it is important to choose a set of properties that are relevant to the biological activity of the compounds and that capture the diversity of chemical space of interest. With this, we'll be starting the quiz for today. So virtual screening is used for whether we use virtual screening for one ligand and one protein, or one protein many ligands, or many proteins one ligand, or none of this. So as I discussed, the virtual screening helps in screening the affinity of large compound that libraries against the target of interest. So based on that, it will be yeah. So it is for one protein and many ligands. So QSAR is based on the notion that activity is a function of a structure, or activity is a function of a molecular properties or molecular descriptors, or activity is a function of physical properties, or all of this. So it is activity is a function of a molecular properties. So here we have discussed several molecular properties. So there are wide range of molecular properties that can be input as used as input variables in QSAR. So residue and atom binding propensities are used in so these are the residue and atom propensities are the probability values that are extracted from the observance of non-covalent interactions of the local regions in the protein structures. So it is a knowledge-based method. So based on the knowledge that you have, based on the observance, we develop these propensities, and then these propensities are converted into the energy values using minus RT ln propensity values to into energetic terms. So which of the following are the measurable molecular descriptors? So here the measurable molecular properties include refractive index, pK, and the dipole moment as well. All of these. So given a simple, I don't know whether this is discussed or not, but how many data points are used for training in a jackknife test for a data of in data points per iteration. So the other name for jackknife test is leave one out cross validation. The cross validation techniques are very useful in validating the ability of a machine learning model, mainly in uh, real value prediction problems. So in the next week session, we'll be dealing about the org programming, followed by the introduction to various topics of machine learning. So what happens in a jackknife test is, consider a data set of 10 points. So initially 9 points are considered as training set and 1 point is considered as a test set. And this process is repeated such that all the 10 initial data points were once observed as test. So that is, initially if you take 1 to 9 as training set and 10 as test set, then you take 2 to 10 as training set and 1 as a test set. So it makes sure that all the numbers once they be as a test set and give us a matrix. Given if the Pearson correlation between two data points is 0, what does it represent? Given the Pearson correlation between two data sets is 0, what does it represent? Okay, so what is the range of correlation values that we can observe? So kindly answer this. What is the range of correlation values that we observe? Yes, thank you for your answer. So the range of correlation values lies from -1 to 1, where -1 indicating the strong negative correlation, +1 indicating the strong positive correlation, and 0 indicating the no correlation. So what would be the application of docking scores? So why we use docking scores? Yeah, in docking we have two concepts: search algorithms and scoring functions. The role of search algorithms is to find the binding site, like scan the surface of the protein, uh, then dock the protein, and also alter its pose. So if search function does that, so what does the scoring function does there? It provides a score which shows the binding affinity. So it's like to rank the active components. So here we have a numerical. So this numerical is similar to the numerical that is available in the assignment. So use the data given below to answer the following three questions. So the IC50 of two protein ligand complex are 15 nanomolar and 6 nanomolar respectively. So we are relating these IC50 values to the hydrogen bond donors, where for protein ligand complex 1 is 4 and 2 it is 3, and polar surface area is 3 and 4 respectively. So try to build a regression model considering a hydrogen bond donors as X and polar surface area as Y, and try to find out the regression coefficient of hydrogen bond donor and regression coefficient of polar surface area. Then I have given a values for a new protein ligand complex. That new protein ligand complex has 3 hydrogen bond donors and a polar surface area of 3. So once we have a regression equation that is available, that is a kind of a QSAR equation, so we can substitute these values into that equation to get the IC50 value of the new compound. So first try to generate the equations. Like IC50 equals to AX plus BY, IC52 equals to A1X plus B1Y, like that. Okay, for those who are feeling trouble in generating the equations, I'll give equations for this. So here the first IC50 value is 15 nanomolar. So I equated 15 nanomolar with its respective hydrogen bond donors and polar surface area values. So 15 equals to 4 hydrogen bond donors into variable of hydrogen bond donor x, that is 4x, plus polar surface area of 3 into its respective variable y. So 15 equals to 4x plus 3y. This is our equation 1. Then we have equation 2 where 6 nanomolar IC50 value is equated to 3x hydrogen bond donors plus polar surface area of 4y. And if we solve, since we have two equations and two variables to find out, so if we solve this to find out the values of x and y. Let us move on to the Google Jamboard. So these are the given two examples. So equation 1 and equation 2. So here I'll try to multiply equation 2 with 4. So now I'll get equation 3, which is 6 into 424 equals to 12x plus 16y. Then equation 1 I'll be trying to multiply with 3, giving rise to equation 4, that is 45 equals to 12x plus 9y. So now what we'll do is try to subtract equation 3 and 4. So 12x will get cancelled. So here I'm making minus. So 16 minus 9y is 7y. 7y equals to 21 minus 21, which equals to y equals to 3. Now we can substitute, sorry, minus 3. We can substitute this y value into any of this equation 1 or 2 to get the x values. So x equals to 15 minus of 3 into minus 3. Just give me 1 minute. Y equals to 15x. Right? So we have 15 equals to 4x plus 3y, and value of y equals to minus 3. So substituting 3 here, we have 15 equals to 4x minus 9, because 3 into minus 3 is 9. Then 4x equals to 15 plus 9, which equals to 24. Then x equals to 24 divided by 4, it's 6. So the value of x is 6 and y is minus 3. So the equation for our IC50 prediction is number of hydrogen bond, the donors or acceptors, number of hydrogen bond donors into 6 plus minus 3 of polar surface area. So initially the regression coefficient, the x value is 6. So now that we have equation, so 6 into 3, the regression coefficient into number of hydrogen bonds, 6 into 3 is 18, and plus minus 3 into 3, 9. So 18 minus 9 gives rise to 9. So this is how. So we got this value by substituting HBD as 3 and PSA as 3. So which is 18, 3 into 6, 18 minus, like plus, but it's minus because we have minus 3 here, 9. So it is 9. Now similarly, I have given some other question. I changed the values here. So kindly provide me with the regression coefficients and try to solve it. So for simplicity, I'm getting the equations here. Try to solve these equations. So similarly, you try to solve this. So the regression coefficients will be 1 and 2. So yeah, your regression coefficients are correct 1, 2. The IC50 value will be 9 because 1 into 3 plus 3 into 2, 6. Overall it will be 9. Here we don't have any negative regression coefficients to talk about. So here now we are having 3 equations and 3 variables to solve. So this I can leave for you to solve. And that's all for today I have. So if any other questions you can ask. The solutions I'll add it in the slide and post it. Yeah, we have some other meeting scheduled from 7, so today it will be a 1 hour class. The solution of this 10th question I'll be posting along with the slides. If no other questions, you guys are free to leave. Yeah, once again, thank you everyone for joining the session. I'm closing the session now. Solutions and upload separately. You guys keep on solving.